Hey there, everybody. Welcome back. This is our final video for Stokes' theorem. And this is a little bit more to just think about line integral and how this kind of shows circulation. We're going to do F dot dr, where F is some vector field for velocity or flow. So it's like a fluid flow. And recall we were doing V dot, or F dot dr was the same as F dotted with T, the tangential component. So anywhere we're going around this closed integral or closed loop C, we've got some tangential component. If we're dotting it with V, the closer V is to being in the same direction as T, the bigger V dot T is. So when V is perpendicular or orthogonal to T, the dot product is 0. The closer this vector comes to aligning with T, the closer we get to the biggest value it can be is when V is directly pointed in the same direction as T. So if V and T were the same vector, that's where it's going to get the biggest. And then like if V is going the opposite direction or is more than 90 degrees apart, it's clearly pointing the other way. Our V dot T is going to be negative. So we've got some velocity field. But if the velocity field happens to manage or match the tangential component of the curve, we are maximizing that value. So it's measuring the tendency of the fluid to move along the curve because V is changing, because T is changing. So T is over here, and if V is still matching up with it, V is closely matched up to it, it's showing that the velocity field is matching the curve. The closer the curve is to the velocity field, the more the fluid is going to flow along. It shows how well it's flowing along it. And that's why it's called the circulation of V around the curve C. And so let's compare it to the curl in a second. Just want to make sure you get that. T is changing as we go around the circle. If V matches up with it all the way around that circle, then it's circulating like a particle around on this thing is moving in a circle around it if V and T are the same. Okay. So let's look at how this relates to Stokes' theorem. Recall the right-hand side of this is going to be the curl of F dotted with N. So F is our vector field V right now. We're going to take a look at a disk centered at P naught with a very small radius alpha. So our surface will be the surface of the disk. And if we do the curl of V at any point inside the disk P, since it's a very small radius, it's not going to be much different than doing the curl of V at a very fixed point P naught. These two are approximately the same, where P is a variable here and P naught is a constant here. It's a fixed point. In a small circle, this curl isn't going to change much. It's got to alpha's got to be very small. So when we're doing this curl of V dot dn, we're evaluating map points. So you plug in X, Y, and Z. But since we can say in a small circle it's almost identical to this, we can treat it as doing the curl of V evaluated at P naught, not just any P, but P naught, and N at P naught. And this dot product is a constant value, and so it's just numbers. We can factor it out, and we've got our line integral of V dot dr. Remember, the left-hand side of this is V dot dr. Oh shit, I got it right there. V dot dr. Going around this circle alpha with the radius alpha is just equal to the curl of V at P naught dotted with N at P naught times the surface integral for ds. That's a 1 left inside there. So we're just finding the surface area of that disk, and that's well known. So the disk is pi r squared. R is alpha, so this becomes pi alpha squared. And that equals our line integral. or V dotted with the tangential component. If I solve for alpha, I'm sorry, not solve for alpha, solve for that curl of V times N, we have 1 over pi times alpha squared times the line integral around the curve for V dot dr. As alpha goes to 0, this circle clenches down in on the point, and we've got the full thing going on. This left-hand side is called the circulation density of V at P naught in the direction of N. And the right-hand side is just called the circulation density of V around C. So as alpha goes to 0, they're the same. And so this is measuring the rotating effect of the fluid around that axis N. So in my picture, N is sticking out of the board. And we're measuring how much this is rotating around it. Okay. It's obviously maximized when we have V is in the same direction as the tangential component. So one second. Sorry, I did regain my bearings. What the hell did I write? Because this looks like I'm writing the norm and I'm not. The curl of V dot N is maximized when the curl of the vector field matches the normal vector. So if I write at an angle and that's N, and we've got our curl of V is like the closer the curl of V, if that's the curl of V, the closer the curl of V is to N, the stronger this is getting. And so when curl of V is parallel, the curl of V is parallel to N, we have that maximized. And so that's why we call it curl. It's circulating or curling around the axis. And then finally, if the curl of V equals 0, V is outward, there's no circulation, which means the fluid is called irrotational because there's no curl. There's no curl effect going on. So that's kind of how they're related. The closer V is to T, the closer the curl of V matches up with the normal component. That's N. And curl of V is like that. Here I've got N is like this. But curl of V is going like that. Nope, like that on that one. And so like the way that the V and the tangential component, the gap they kind of have is the same relation that the curl of V and N have. So the closer V is to T, the closer curl of V is to N, and this gets maximized. And that's where we get circulation. That's it for Calculus 3. I will have another treat for you later, non-dimensionalization. It's kind of upper game stuff beyond the scope of this class, definitely. But it's really neat what they do for it in physics, like Navier-Stokes equations and fluid dynamics. Peace.